Good morning, Fancy Meat Computers. How is everybody doing today? I hope everybody's doing well on this fine morning in the middle of July. I have a question. Sorry, I would have asked this last lecture, but I had to work. If you have a long pointer, for example, and you read it as a char pointer, would it only read the first 4 bytes? Well, char would be, a char is only 1 byte, actually. Like, it's the pointer type that tells the computer how far along the memory is to move. Yes! Yeah. So, let's say, just for example, and C lets you do this kind of stuff, too. Let's say you had a pointer to a long, which is a long integer. Actually, yeah. So a long int is 64 bits, which is 8 bytes. A normal int is 4 bytes, which is 32 bits. And a character is only 8 bytes, typically in C. So if you were to take a pointer, cast it as a different pointer type, you would have the same memory address. But yeah, C would interpret that as now being a character. So what it would do is it would take, if you were interpreting it as a character, it would take the first 8 bytes of it, call that a character, forget the rest exists. And that can have unpredictable consequences, depending on whether or not your system in the back end is doing big endian or small endian. Like, you might get the top byte or the bottom byte. It really depends. Some systems you get the top byte, other systems you get the bottom byte. But yeah, that's a good question. Yeah, that was about pointers. So, with respect to announcements, we don't really have much in the way of announcements, with the possible exception, if anybody noticed, in the middle of the week last week, I released Assignment 2. So Assignment 2 is now up and available, and if you want to get a start on that, then please, I would recommend it. Now that you know some pointers, well, you know what? My personal recommendation would be to not start on Assignment 2 until you've had tomorrow's lecture, because tomorrow's lecture we're going to be talking about strings and file I/O, and there are, Assignment 2 leads off with questions of that type, so, if you already know it, then feel free, go to, but if you don't, then I would recommend waiting for tomorrow's lecture. But yeah, but that's not what we're talking about today. What we're talking about today is highly relevant to the labs that are going on this week. So we're going to talk about Makefiles. There we go. RIP headphone users, as usual. Also my wife in the other room. RIP my wife. She's like, "You're so loud when you're lecturing." And I'm like, "I know, I can't help it. I'm just so enthusiastic." It's okay, though, because little baby Felix makes his presence known on stream every once in a while, too. Yeah, cool. Yeah, C is kind of funny like that, right? Like, a lot of people sort of think... a lot of people think of types as being categories, right? Variables can be put into one category or another depending on what type they are. C doesn't really recognize category distinctions between memory like that. Everything to C is 1s and 0s in various sizes, right? Even a character, ostensibly, even though you see it as a character, in C, all it sees is 1s and 0s that it feeds off to some subroutine somewhere, the character that pulls up the character map and produces the the actual character and displays that on screen. That's that's like something else to C, you know? It's like, to C, like, C has absolutely no problem freely converting between integers and characters, for example. Which is why, when you're programming in C, you should always be aware of the byte width of the data types that you're using, because that's the only thing that C really cares about. If I were teaching my mechatronics class that I taught last year, the C-based slides are actually borrowed from that course, in large part. I've trimmed them down because we only get 2 hours lecture per week. But if I were talking to the mechatronics class, I would say, and you should always be aware of your byte width anyways, no matter what you're doing, because you're often going to be programming in embedded systems environments, and your memory actually matters. But, you know, neither here nor there. So, we've got 8 people watching today. 9 people. Oh. I guess everybody's all slogged out from the 2 labs plus the assignment that was due for this morning, hey? People who submitted MSAFs for that certainly got the best bang for their buck that they're likely to get in this course. So, Makefiles testing and static analysis. We're going to talk about Makefiles. So if you don't know what a Makefile is, the general idea is automation. The theme of the next 2 labs, the 2 labs that we have this week actually, the theme is automation. Typing stuff by hand is lame and prone to errors, so we're going to learn how to get the computer to do our work for us. You know, largely speaking, the programmer's life should be primarily figuring out how to make computers do your work for you. But before we get into Makefiles, we have to talk a little bit about we have to review the compilation of C programs, which hopefully the lab that we had last week on libraries, we were talking about compilation pretty heavily during that. Hopefully that serves as a good grounding. So, recall the stages of compilation. We start with source code. The preprocessor expands the code and deletes all of the comments, processes any macros. The compiler parses and produces the abstract syntax tree, right? Then we have the assembly that assembles the machine code from the abstract syntax tree. And then the linking process links our object code up with other object code files that are used. So when you use a function like printf, right? Printf, the object file for printf is held somewhere in the misty realms of your root folders in Linux. The code that, like the actual code that constitutes printf, doesn't get thrown in until the linking phase. We can actually stop the compilation process at the assembly phase, and we often want to. So object files, right? You've been using object files over the course of the lab. I think it was lab 6 used object files quite extensively in order to construct libraries. I might be getting that inverted. It might be lab 5, but it doesn't matter. Oh, geez, I just about knocked over my tea. Ha! You should screen cap. I gotta see that. Let's see. Oh, am I gonna miss it? Am I gonna miss it? Me almost knocking my tea over? Ha! This is gonna be funny. Oh, yeah, there we go. Yeah, anyway. So, object files. So what is the point of an object file? what is even the point of you? Well, an object file is machine code that is compiled from its source code, but without the code for any called functions in other source code files. So, in a very real sense, there is a correspondence between the object file and the source code file that does not exist between the source code file and the executable file. The executable file, like the thing that actually runs, it needs code from other sources in order to actually run. And because it's an executable file, everything is contained within the executable. An object file, ostensibly, the assembly code that exists inside of the object file is only that assembly code which is generated from the source code file itself. So this can be useful. Rather, an object file contains links to the needed functions in the needed files and libraries. So let me just navigate down. Documents, Master Teaching 1XC3. Yes. The summer term. Work. So, for example, I think, let me just, I think if I find the stuff I was working on last, the stuff in Lab 5, I think it is, Lab 5? Nope. Lab 6, it was Lab 6. Yeah, here we go. Here are some object files. So, if you consider, for a moment, sea shanties... before I came up with the delightful pun, sea shanties with a C. If you actually take a look at the object file itself... Maybe a binary file, see it anyway, yes. So, this is what a binary file looks like, of course. There's a lot of junk going on here, but you'll see that since we're rendering this object file, which is a binary file, as ASCII text, any parts of it that happen to already be coded in ASCII text, that will be readable and visible inside of the object file. And you'll notice that there are a few things that are in there anyway, like the version code for GCC, and a few other bit and sundry items. Yeah. So, essentially, in all of this mess, there are links to other object files. And of course, you know, again, it's garbledy-gook to us, but to the computer it makes sense, and that's all that really matters. So object files are binary encoded, not character encoded, so there's no point in trying to look at them with cat or less, even though your professor just did so. By compiling an object file for each source file separately, the object file only needs to be updated if the source code is updated. This can produce a massive speed boost in compilation time. So one of the things that we're going to be getting into over the course of this lecture is the idea of making our processes more efficient, right? Now, it's entirely probable that you haven't really run into source code compilation time problems so far in your career. In particular, given that a lot of what you've been doing has been working with interpreted languages rather than compiled languages, remember, a interpreted language like Python, it feeds your source code into the interpreter one line at a time, so it's compiling as it goes. That means that you don't have to pay the upfront compilation cost, right? However, with a compiled language, the compilation process takes time. It's unlikely that anything you did on Assignment 1 or any of the labs so far, the programs haven't been big enough for you to have noticeable compilation times, right? However, if you're working on anything real, like, GCC itself or Clang or, any, I can remember my my own thesis project. It's written in Haskell, but the compilation time on it is just about one game of Hashiwakakero on my phone, which is it's a fun little bridge connecting game. If you look at the game that I released on Steam in January, that's actually a adaptation of it for hexagons rather than rectangular, which is normal. But anyway, about a minute and a half, and that's the efficient compilation. If it had to compile every source code file each time, it would probably be more like 10 minutes, right? And that's 10 minutes is 10 minutes. But if you have to, if you're debugging code and you're making a small change and you have to wait for it to compile to see if the change took effect, and if that's your workflow, then the amount of time that it takes your code to compile, that can be a substantial portion of your workday. And of course, our goal, as with all things, is to be the best employees possible, and the best employees try to be working a maximum amount of time during the day, and that means reducing the amount of time that you have to spend waiting for things to compile. So then object files allow you to pre-compile source code files within a project, and they only have to be recompiled if they've been updated, right? Otherwise, the old object code can just be integrated into whatever new build you're doing of your software, and it doesn't need to be recompiled. So you can save a lot of time, ultimately. Objection. Phoenix Wright, etc. Object files correctly require using object files correctly requires effort. We can combine batches of source code files to we can compile batches of source code files to object files using glob patterns. We're going to talk about glob patterns next week. And the C flag. This is a glob pattern. But when we then go to compile our program from the object code, in GCC, we have to include every object file that we want to compile the code with in our GCC invocation. We must manually include our object files, which is tedious and time-consuming. So, we're saving compilation time, but losing time to longer commands, which, might actually be more annoying. There has to be a better way. So, your first instinct with this is like, oh, well, if I have a command that... pardon me for a moment. Allie, that's a delivery! Yeah. Sorry. So... where was I? Oh, yes! So your first instinct might be to use a shell script, right? If you have commands, which must often be repeated, this is the typical situation in which you would introduce a shell script. particularly if they're long and difficult, and you only have to get them right once if you write it down, right? That's where you would use a shell script. But Makefiles are better. So a Makefile is it's a way that we can automate our compilation process that is much more fluid and adaptable than simply sticking out all of our compilation, all of our GCC invocations inside of a bash script. So make is a GNU program. If you type where is make, it's in user/bin/make. So that's where it is. Makefiles, they only compile this. They're a way to only compile the source code files that need to be recompiled in order to produce the executable. Right? So it does this. The way that it works is you set up rules, and when you invoke a makefile, or when you invoke a rule in a makefile, it will only compile the rules that it will go through the rules that are needed to compile to execute the rule that you want executed. Sorry, I'm not explaining this very well. If it doesn't need to be recompiled, it won't recompile it, essentially. So it's faster. The way that it actually works is it checks the time at which the source code files were saved and compares that to the dates, to the timestamp of the compiled object files, right? So, like every file has a date stamp. It has a timestamp on it, right? The time at which that file was last modified, right? So you can tell that something needs to be recompiled if it has been touched since the last compilation. And you know the time of the last compilation because the compiled file will have that date attached to it, right? So make requires special configuration files called Makefiles, which tell it which files to compile, which compiler to use, and many, many other things. Makefiles are not bash scripts. Bash script syntax is not applicable largely to Makefiles. That's a very important thing to know. That's an important pitfall that a lot of people hit. Makefiles are different and distinct from bash scripts. Are there any questions so far? I'll give you guys a moment. All three of you. Ha. Wow. If even one person is listening, they still get the full lecture. Cool. All right. There we go. So, sudo make me a sandwich. Makefiles are composed of rules. Rules have three components: a target, a prerequisite, and a recipe. A big fat thumbs. There we go. Hello. Hope things are going well. So, a target can be one of three things. It can be an executable file, it can be an object file, or it can be a so-called phony target, which functions as a special command. So when we write Makefiles, we often include in Makefiles certain subroutines which are not necessarily strictly compilations, but are otherwise useful to, they're things that you would need to do often with, just things that you might want to automate. We often include those in Makefiles as well. These are things like clean commands or compile all commands. So the prerequisites are the files that are used as input to create the target. These can either be source code files or object code files. When it's an object code file, basically the way that make works is if you call a rule to be executed, it will check all of the prerequisites first and make sure that they exist. So, if you have a source code file that you've put as a prerequisite, but make can't find it, it'll throw an error at you. And it'll say, I need the source code file, which probably means you just failed to locate it properly within the make file itself. If it doesn't exist, make will see if there's a rule for it. So Makefiles will typically have a lot of rules. And so if I need A.O, B.O, and C.O, and none of those exist, make will it'll look to see if there are rules to make A.O, B.O, and C.O, and if there are rules, it will execute those rules. And it does this recursively, so any prerequisites that A.O has, it'll go through that prerequisites list first, and then, pass things up the chain. You can't get away from recursion, no matter how you try. So, yeah. And it does this all automatically just by checking whether file... All it's doing is checking file existence and timestamps, and it's building all of this in together. And just like you could build a C program to do all of this stuff, you could build a bash file that performs all of this work, right? Like, we know how to check to see if a file exists using using a bash script. We can look up things timestamps. It's not that difficult, right? However, these are commonly needed these are commonly needed things. So, back in the early days, the Greybeards decided it would be useful to have a command that you could, organize these processes somewhat more easily. And, moving on into the future, this style of compilation management is the same thing that's used by, various package managers. In Haskell, if you're using Stack, I think it's called Stack. If you use Stack as a package manager for Haskell, it runs through compilation of Haskell source code in much the same way as this. Docker is another one that does this type of compilation. Makefiles are, somewhat old and primarily these days used for C, C++. Like most other languages will have their own version of Makefiles, but with varying degrees of automation. But if you're talking C/C++, make is where it's at. So anyway, the prerequisites are files that are used as input to create the target. A recipe is a bash command, or a series of bash commands, that make performs to create the target. So the recipe is how you make the target, right? Each recipe line must be started with a tab character. Spaces are invalid syntax for no reason whatsoever. That's just the way it is. If you use spaces, it's wrong. So, here's a simple example, which you may recall from Lab 6. So the files that we used in Lab 6 to create static and dynamic libraries were top.c, sums.c, products.c, and cshanties.c. We used a lot of fancy compilation methods to create static and dynamic libraries, but you can also compile these using more simple invocations of GCC, such as GCC top, output top, top.c, sums.o, products.o, and cshanties.o. So, Makefileification. If we write rules to produce all of the object files and the final executable into a Makefile, this is what we would get. So, top, cshanties, products, and sums. See, these are all the object files that we need. These are the compiler invocations that produce the object files. And if we want to compile top, this is the same invocation from the other page. Let me see where I might have put it in the slides directory. Topic 9. This is why it's terrible and a terrible idea to include spaces in any of your directories. Yeah, there's a Makefile. So, a couple of technical points. The way that Makefiles work as an invocation is if you call the make command, it will search the current working directory for a file that is called Makefile, just like this. It will automatically look that file up and do the stuff that's in it. You don't actually have to pass the file name to make. As long as you've named it Makefile, Make should be able to pick it up automatically. So, if we take a look inside Makefile, it's probably got some extra stuff in it. Yeah, it has some extra stuff in it that we're going to get to later in the lecture, but in general, the way that it works is you make top is up to date. So we gotta touch some files. Touch sums.c, touch cshanties.c. There we go. So what the touch command does is it updates the timestamp on a file to the current time. We also use it for file creation, but it also, you can use it to update a timestamp without actually having to perform any modifications of the file. So, if we make top, notice it runs, it tells you what commands it executes. So it executes 2 GCC invocations for sums.o and cshanties.o, and then one for top. So there you go. And then we can execute top, and you can see that it works. Sherbrooke should probably be capitalized. So that's how a Makefile works. Yes. And now usage that I just showed you. Now that we have our Makefile in place, we can start compiling. To compile the default goal, just type make. So the default goal is the first rule, and if you let's touch sums.c. There we go. If we just make, then whatever the first rule in the Makefile is, that in this case it's top. That rule is the default rule that, just typing make, that'll invoke it. You can compile any of target in the file by specifying the target. So you can make, like, any of the object files you have a rule for. You can make, the top file specifically. And you can also invoke a phony target, again, just by typing in the name. Nothing could be more simple. So this Makefile that I've got here doesn't include a cleanup routine. So let's put one in just to see how it works. I'm going to do this in Emacs. Makefile. I should do it in Get It, actually, because the print on Emacs is so small, and I can never figure out how to adjust it. Although an Emacs veteran would probably be like, oh, it's just Alt-I, Control-V, Control-Q. Because Emacs has a shortcut for literally everything. So, clean. That's the name of our rule. Prerequisites, none. Leave it blank. Tab. Now, what do we clean? What do we want to clean? It's typical. So cleanup routines typically will remove any object files and sometimes the executables as well. So rm star.o, rm star tilde. You'll notice if you take a look in this directory that there are a few files that have a tilde after them. Those are backup files that are created by Gedit. There's like autosave files. So we're going to remove the autosave files as well. All right? So we just make clean. And then you see we have just our source code files left. You see how that is cleaner? It is cleaner. I'm not crazy. I also don't have obsessive compulsive disorder. It would be impossible for me to function as a human being if I did. Because I live, Anyway. So, if we make, again, you'll see that the object files come back, and then we can just clean. Make clean. There we go. So you might be getting the impression that these things are not all that difficult. Oh, chat is disconnected. Uh-oh. Is my stream disconnected? Okay. Okay. Somebody, if you could say something in the chat just to make sure that the chat is coming through. Give me a thumbs up if this material makes sense. Nothing could be more simple. So, yeah. So I'll just go through the slide then. On default invocation, i.e. just calling make with no arguments, that will make the first rule as it compiles the target. Good. Oh, good. We've got people coming through. Therefore, your top file should be at the top. So whatever the end goal of this whole project is, that's normally the top rule. Whether the target is default or specified, make recursively processes the rules for all prerequisites of the target value. Make chat test. Ha! Yes! Yes, indeed. If the source file is newer than its corresponding object file, or if the object file doesn't exist, make will produce it. For testing purposes, touch updates the timestamp on a file. This is basically all the stuff that I've just told you. Any file which needs to be linked to another object file will be regenerated as well, if any object files it needs are newer than itself. So, basically, the way that make propagates recompilation is if any prerequisite needed recompilation, it will recompile anything that uses it. Ugh. Pardon me. Yeah. Yeah, anything that it uses will be anything that uses something that is recompiled will be recompiled, regardless as to whether or not, in our example, adjusting the date stamp doesn't actually change the object file, right? There's not one bit different between the object file before and the object file after recompilation, but Make doesn't care. It just looks at timestamps because that's fast. So, variables. Makefiles, batching, and shell scripts. Typing everything by hand. I finished my work while you were still complaining about it. Programming is hard. Generally speaking, programming is hard. Like, it's math, and math is hard, no matter what they tell you. But, you can make your life a lot more difficult than it needs to be, and a lot of the problem people have with programming is that they don't, they learn the basics and they think the basics will carry them through to a career, at a certain point, your knowledge of programming has to get beyond if statements and while loops, and the more stuff you learn that makes your life easier, the easier it becomes for you to program, and the less time you have to spend on the assignments. So, I'm not saying that it's necessary for you to write Makefiles for all of the questions in Assignment 2. I'm saying it might be useful for you to write Makefiles for all of the questions in Assignment 2. We're not okay, in seriousness though, we're not marking for Makefiles in Assignment 2, but now that you know what they are and how they work, it would be foolish not to use them. So, let's talk about variables. As with so many things in life, we can make things once again simpler in the long term by complicating things in the short term. So, Makefiles support variables, which are similar in many ways to the variables in shell scripting. Actually, they work highly similarly to the variables in shell scripting. One might say they work exactly like the variables in shell scripting, with one exception. In Makefiling, when you're writing a Makefile, the enclosing the variable's name in round braces is considered good etiquette, whereas that's not a requirement of style in Bash scripting. That is a requirement of style in Makefile making. So that's the only thing. It's a stylistic point. It still works if you leave the braces out, but it's included because it makes it easier to read. So variables, once again, need the variable substitution operator, $, to work. Once again, variables are character substitutions, but with Makefiles, they're a little bit looser on the white space. Like a tiny bit looser on the white space, but in general, it's still direct character substitution into commands. Yes. You also don't have to worry about not leaving some white space this time around, but don't go overboard. When set up correctly, variables let us control many things about our compilation process from a few lines at the top of the file. So, number 1, let's abstract out the compiler. If we assign CC to GCC, then everywhere we have GCC appearing in our file, we can replace that with the compiler. Basically, this means that we can change compilers without having to edit every line of the without having to edit many lines within the Makefile, right? This is not, it's not typical that you would need to that you would need to compile for multiple compilers, or that you would have to compare compare the results of different compilers, or a project would migrate from one compiler to another. That would be pretty rare, actually. Generally speaking, it's a terrible, terrible, terrible idea to try to migrate a project from one compiler to another, even if it's the same language. Just don't. Just avoid that at all costs. Just don't, please. I'm begging you. But imagine something like this. Imagine that you were working for a company and you were told, listen, I want you to benchmark this product for as compiled with GCC, Clang, and Microsoft's C compiler, whatever it's called, WinC or something probably. What you would like, the effective way to do that would be to write a Makefile where the compiler itself could be controlled using a variable, so that you can just, modify one line and bing, bang, boom. You could even probably script the, you could script out that whole process, actually. But yeah, so hopefully that's reasonably straightforward. We can also abstract out the compiler flags. So if you'll notice, in the previous example, each one of these uses the WALL flag, which is warnings all, and they all also use the output flag to specify the name of the output. We can take both of those things, extract out, we can put them in as a flag, right? And depending on how many flags you want to use, this would be an easy way to, for example, turn on O3 optimization on all of your compilation processes all at once. But, the flags which are not used in every single compilation process, those would have to go before now, because remember, the O flag expects the next thing given to be the name of the produced file, so that still has to be the case. Incidentally, Makefiles support comments as well. You use the octothorpe character just like in Python. To my knowledge, Makefiles do not support multi-line comments. They might, though. Who knows? Another thing that you can do is you can abstract out the list of objects. You can also abstract out, like, if there are multiple executable files that are contained within the Makefile, then you can have a list of all executable targets, and that can be, that can also be the case. So yeah, if we abstract out the objects, you notice we can perform that replacement here and here. So, this is getting shorter. So yeah. Although it isn't required, it is conventional to use a cleanup phony target, which deletes files during executable generation, but which are not needed afterwards. So specifying no prerequisites makes this a standalone rule. So it does not require any prerequisites. It doesn't need to see if anything else exists before it does this. The F flag on RM means force. That stops RM complaining about requests to delete non-existent files. Like, if I have, if I try to RM doesn't exist, .c, never mind. Let's not include an apostrophe there. RM cannot remove doesn't exist. However, if we say force it, then it doesn't complain. Another one is all. Another phony target typically included is all. This isn't necessary unless a makefile has more than one final target. So if we had more than one final target, and not just top, then it would make sense to have an all, but we can also have an all targets variable that specifies all of the executables we need to make, and then all just makes all the targets. You don't need a recipe, because the only purpose of this rule is to activate multiple other rules from one rule, right? The all rule doesn't typically do anything by itself. It just queues up all valid targets for regeneration by making them prerequisites. You might put like an echo in there for it to print, now compiling all targets, something like that. You know, if you like things to be verbose. A certain amount of verbosity can go a long way, actually. Are there any questions about that? I will pause briefly so that we may discuss questions that you may have. This doesn't seem too bad, right? This is, like, not too bad. Hopefully this isn't too bad. Makefiles are not as complicated as bash scripts, but as he was preparing this lesson and the labs last week, your professor found out that one thing that you can't do inside of a recipe is use bash-style if statements. So, but, yeah, good, excellent. So you can't use bash-style if statements inside of one of these recipes, but you can call a bash script inside of a recipe. So, you know, there's a part in the labs this week where, I think it's like, it's some operation like if a directory doesn't exist, create it, which, you know, that's a very, very short bash script, but the if statement wasn't supported by Makefiles, so the way that I got around making my solution to the lab is to have the Makefile invoke a bash script that creates that directory. So, there you go. All of these tools connect up to each other, right? It's Lego. It's just one goes in the other. You gotta think in terms of connect things up. Each one of these things is a tool. Each tool has its use. You know? Like, this is the Unix design philosophy. Each command, each thing, each function does one thing well. And it's your job as the programmer, as the operator of the operating system, to know how best to put the tools together to accomplish the task you need. It's like plumbing. Don't use an adjustable spanner when you need a monkey wrench. So, if you don't know what a spanner is, it's the type of wrench most people think of when they say wrench. So it's like the one that looks like that with the handle. Anyway. So now that we know some stuff about Makefiles, let's talk about testing. So, testing is good. Testing is lovely. Everybody loves testing. Well, no. Everybody hates testing. Testing is tedious. However, testing is tedious and routine. So, it is possible for us to write routines that allow us to do testing in a quasi-automated fashion. So, automating things is both efficient and satisfying. So let's automate one more tedious programming task. Testing! When testing a program, we compare the expected output of our program to the actual output of our program. Of course, this only works if both outputs were produced from the same input, right? Remember, think back to 1MD3, think about when we talked about testing, think about when we talked about, Black box testing versus white box testing, right? Remember these terms? Remember, in order for testing to be accurate, we need to always start from the same input and expect some output, right? We need to have input-output pairs that represent correct behavior so that we can compare our program to them, right? You need requirements to be able to test effectively. You can't just run the program and be like, oh yeah, the program works. It didn't crash, so it works. It's good. No. No! That's not how testing works. That's bad programming. You wrote a bad program, PD. Anyway. So the expected output can be generated by a number of processes. Humans can design the output. A different, perhaps less efficient algorithm could have produced the output. If your object is to increase the efficiency of, if you want to increase the efficiency of a program without modifying its input, without modifying what the output looks like, then, it is permissible to use the output as produced by the old version of the program to test the new version of the program. That's permissible, so long as the original program was implemented correctly and was tested and it was fine. Another place that testing can or expected outputs can come from is customer requirements, although you will find, most of the time, that customers are not sufficiently precise to be used directly as testing requirements. Customers normally communicate in human language, and human language is notoriously imprecise, and imprecise human language is not typically suitable for testing because it's not sufficiently rigorously mathematical. But anyway, so different strokes for different folks. Diff is a command. So if we've got file1.txt and file2.txt, this is what these files contain. If you look closely, you may notice that there is a difference between these files. One of these things is not like the other. We have a command that can tell us what the differences are between files. So, diff tells us we have a difference in line 4. So, special note on this side says 4, special note on this side says 5. Diff. It doesn't really make a lot of sense to diff things that are very different. So, diffing Makefile against sea shanties. Pretty much the entire files are different, right? Yeah, exactly, the entire file is different. However, if we diff two files that are similar, so diff sums.c and products.c, you can see, so to speak, that there's, there's not so much difference. Basically, the primary difference between sums and products is the name sum and the name product, and the fact that sums and products use multiplication and addition, respectively. Respectively? Yeah. So, diff. So, okay. So, diff is a command. This is a command that's cool and fun, and is probably the way that Git does a lot of your managing of merge conflict. But how do I use this for testing? Well, my friend, if you can coerce your program to route its output to a file, then you can construct what that file should look like, and then compare the expected to the produced using diff automatically inside a bash script or inside of a Makefile. And it will just report to you which test cases were failed, which ones well, you have to interpret a difference as failure, but that's a relatively simple mental step. So, introducing diff. Up to now, we've been comparing our expected and actual outputs manually. This is, or in the case of 1MD3, using equality operators that people can break. This is, however, slow, tedious, and a bad use of human resources. The diff command automatically reports the differences between two files. Combined with output capture in Bash, we can run a program, collect its output, and compare it to a pre-existing file that gives us our expected output. So, this is the procedure. You run top with its output being routed to, say, top output.text. Right? Now, the thing about output capture is that it also suppresses the standard output, right? So you won't see it. You won't see the output yourself, but you will see it in the file. So if we cat top output.text, aha, interesting. It didn't work for some reason. Probably had to wait till it was finished or something. Well, at any rate. So this also works with printf statements, right? This guy will capture anything that you send to standard output. It'll dunk it into a file. Being dunked into a file, you can then diff it. Naturally, we can integrate this sequence of commands into both bash scripts and Makefiles. Cool. We can also use exit codes, right? So, exit codes are used by commands and programs to indicate success or failure, right? So, if, for example, you remember it was, what is it? User bin time. Yeah? Yeah. User bin time rm doesn't exist. So if you try to remove something that doesn't exist, it should complain at you. It should write to standard error. Command exited with non-zero status. Oh, and I need verbose on time. There we go. So, if you remove something that does exist, like a.out, for instance, exit status is 0. 0 means I terminated normally. I did not require, I encountered no errors. Right? Exit status of anything other than 0 indicates a problem. What the exit status is and what it means will vary from program to program. Each program will have, you'll be able to look up in the documentation somewhere, there will be a chart, there'll be a table of exit status codes and what they mean for each of the different processes. If it's not sufficiently obvious, or if it doesn't give you any useful, anything useful to say about it. Yeah, anyway. So the way that you produce an exit code is in C, just return something other than 0 from main, right? Whatever the return value is from main in a C program, that gets sent to bash, right? That gets sent to the environment in which the C program is running. And there are a couple of ways of producing this other than using a return statement. In bash scripting, the exit status of the last command to run is stored in the special variable $? I guess I will interpret that as, huh? So, for example, if we have cpcheck.sh, let's say we're copying from one place to another that are given, these are being given as command line arguments to the bash script itself. If this guy is equal to 0, if is equal to 0, then we echo copy succeeded. Otherwise, we echo copy failed. So, if we use this script to try to copy from none.c to some directory x, cannot stat none.c, no such file or directory, and the thing says copy failed. Whereas if it was a valid copy, if copy worked, if copy returned 0 as its exit status, we would see copy succeeded. Cool? So exit status. It's important. Like right now, we're learning how how commands and programs communicate with each other, right? And we can use how they communicate with each other to perform functions. So, the assert library. We're going to be this is C programming specifically. Output comparison using diff is great for automated black box testing. However, many or even most of the properties we may wish to test are internal to the program. So, again, you've got some options, right? One way of displaying internal program details is using printfs. Although at this point you should know that very well by now. Another way of doing that is using the assert function, which is contained in assert.h. So the assert function allows us to perform testing within a C program. How it works is, we'll get to the example. You just give it a Boolean condition, right? At runtime, assert will evaluate that Boolean condition. If that condition evaluates to true, everything is fine. Execution continues as normal. If the assertion comes out false, then the program is immediately terminated and a non-zero exit code is returned to bash, right? So if you remember assert statements from Python, it's similar, except rather than producing an exception, which if it's handled is fine, right? In Python, if you handle the exception, then you could continue your program. In C, if you have an assert statement which fails, that is just an immediate program crash. The thing crashes to desktop, so to speak. This is actually because it invokes another function called abort. We don't need to talk about abort. It's pretty internal. You can call it if you want, but again, that's like, please crash my program. And most of the time, you don't want your computer to crash your program, so yeah. In addition, assert reports the following to standard error: the expression which failed the test, which is very useful to know, the line number of the failed assertion, and the file that the assertion is in. So, we've got an assertion example. Enter the letter X or else, and then it scans for it, and if the first character entered is X, then it prints good job. If not, then it aborts the program. So I think, yeah. Let me just make sure that this is the same file. It is the same file. Good. So if we Compile that file. 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 There we go. A dot out. Enter the letter X or else. X. Good job. Enter the letter X or else. Make me. There you go. An assertion on line 8 in main, which is this, failed. Right? File name, line number, function name, and the particular condition. If you need more information than that, like what the actual values of the files are, you know now at what point in the file you can insert some printf statements to be able to actually have the program barf up what the actual values of these things are. Coolio. So, here's an application. Auto grading. System program problem detected. Do you want to report the problem now? No. Because I'm a bad person. So, application auto grading. This is how the auto grader for the assignment that you just submitted works. First, number 1, we have a program which replaces your main function with one of our own design that calls your functions for certain inputs and makes assertions about the outputs that it receives from those functions. Yeah, so this is why we say don't put anything you want marked inside of main. Next, we compile your program. Any code that fails to compile is reported as a failed test case, right? So, because GCC also returns a non-zero exit status if compilation has not turned out, right? We can detect the exit status of GCC and use that to determine whether or not your code failed to compile. If your code fails to compile, then it's not worth any marks. In fact, on the assignment, there are a certain number of marks available if it compiles, sort of regardless as to whether or not it actually works. So, you know, you get like 1 mark out of 8 just for having it compile. Don't tell me I'm not generous. So, we then execute your code, right? You know, we run it. As it's running, if our inserted assertions fail, that test case is considered to have failed, and 0 is recorded for however many marks that test case was worth, right? So, you know, like we'll do this process once for each test case, right? Like if you have a question that's worth 8 marks, you might have between 4 and 8 test cases. I typically don't do test cases that are worth more than 2 marks, but, you know, 2 marks is not uncommon for a test case. So for each test case, it tries to compile it with the inserted code and then executes it with the inserted code, and the inserted code is different each time because it's a different test case, and that's a secret. You're not allowed to know. So, if no assertions fail while we're executing your code, then that means the test case passed, and you get however many points the test case was worth. We run several test cases per question. And, you know, as I said, in this manner, we can process each assignment in about 1.5 seconds. So, and of course, we write a script so that all of the assignments are processed in sequence. Like, we batch process all of the assignments. So, actually, I checked with Mark about this number, and Yeah, it was like something like 120 seconds to do a class of 80 students for to do all of their to mark all of their assignments. And let me tell you, from a TA resources perspective, marking is like extremely time intensive. Ask Nish. Um, like even if you can get it down to like 10 minutes an assignment, you know, um, if there are 50 students in the class, 50 assignment submissions, that's 500 minutes, right? And you know, that's, oh my goodness, where's my calculator? 500 divided by 60. What am I talking about? I'm sitting in front of a calculator. $500 divided by 60. Yeah, so that's about 8 hours of work, or one full workday. And considering, like, in a normal semester, a TA contract is worth 10 hours a week, and in the normal semester 10 hours a week, in the summer semester 20 hours a week. Like, if there are you know, if there's one assignment or lab to mark per week, yeah, then that's pretty much an entire, that's one TA's entire job that week, is just to mark that assignment. And that doesn't leave a lot of time for example, Piazza posts, right? Or communication emails. And God help you if there are lab duties on top of that, you know? So, like, I really see auto-grading for these types of courses, you know, courses in which it makes sense to do auto-grading. Like, this is a programming course, so obviously it's easiest to auto-grade programming. But, you know, the one thing is, you have to make sure that the man hours that are being freed up by this type of technique are then being turned toward the student, right? Like, you guys should be benefiting because we use these types of techniques, right? We shouldn't just, you know, become lazy and spend the time playing Minecraft. But yeah. Anyway. Damn, all that time makes it just boom, graded. Yep. Yeah, I mean, you know, take into consideration it does take time to write the script, right? But the time it takes to write a script for a class of 100 students is definitely not, or, you know, even for a class of 50 students, it's not going to be 8 hours, right? So yeah, like, that's the power of automation. So let's switch gears now a little bit and talk about static analysis. You may notice that C's compiler errors are not as explicit as Python's. When you get a compiler error in C, you don't necessarily know what the heck's going on, right? C doesn't, like, sometimes the compiler errors are very good, and sometimes they're just baffling, and you have no idea why they're giving you this. So the functionality to be able to see all of these things that other compilers complain about, it exists, it just doesn't, it's not in GCC. You have to go elsewhere to look for it. Static analysis engines are pieces of software which analyze code without executing it, right? So if you have to run the code to analyze it, that's called dynamic analysis. So benchmarking is dynamic analysis. Static analysis is merely looking at patterns in the file, like in the syntax of the file itself. So another way of, like, if you want to link it back up to our phases of compilation, right? The way that static analysis works, you use a preprocessor, you use a compiler to get it to the level of an abstract syntax tree, and then you judge relationships between the various elements of the abstract syntax tree. I personally know a certain amount about static analysis and static analysis engines because I wrote one for my thesis for a hardware language that nobody uses. So, during static analysis, source code is preprocessed and parsed, but no executable code is generated. Instead, the abstract syntax tree itself is analyzed. Common patterns which normally indicate bugs or problems can then be identified and are reported to the user. So, introducing CPP check. To quote the CPP check manual, CPP check is an analysis tool for C/C++ code. It provides unique code analysis to detect bugs and focuses on detecting undefined behavior and dangerous coding constructs. The goal is to detect only real errors in the code and generate as few false positives as possible. CPP check is designed to analyze your C/C++ code even if it has non-standard syntax, as is common in, for example, embedded projects. So, if you want to check out CPP check, which I highly recommend considering I'm teaching it to you, so I'm expecting you to be able to use this at the end of the course. It's fortunately very easy to use. You got to install it. This is the manual. If you want to install it, you go to cppcheck.sourceforge.net. SourceForge is like that. This should be, if you don't know about SourceForge already, SourceForge is like it's a repository of open source software projects. All the best stuff is in SourceForge. If it's not in SourceForge, be suspicious. You should be suspicious of everything, but you should be more suspicious of stuff that's not in SourceForge. So yeah, you've got various ways of installing. Do I have slides on installation? I do have slides on installation. So, to install CPP check in Debian family Linux, like Ubuntu, Mint, and MX, it's sudo apt-get install CPP check. In Fedora, you use yum to install. To install on Macintosh, it's brew install CPP check. Brew is your package manager for Macintosh, I suppose. If you're a Pascal server user, it's already installed. I had Derek install it last week. If you're working on Windows, you can find the installer at cppcheck.sourceforge.net. Those wishing to have CPP check installed directly into their brains will have to wait for driver support. So, it's kind of a magical thing, right? Because it's like, so it detects errors, it detects bugs, right? It's bug detection software. But it's important to understand what the limitations of it are. Or maybe I can give you an example first. ls, there we go. So, so I've got this file, badcode.c, and I'm going to cpp check badcode.c. I've got two flags that come up. An error. I'm dividing by 0 here. Here. One of these places. And number 2, on line 5, I've got array A5 accessed at index 10, which is out of bounds, which, if you look, I've got an array of 5 elements. I'm accessing element 10. That is an out-of-bounds error. And it's interesting. CPP check calls this an error, and but C itself doesn't do bounds checking. So, personally, it doesn't take a lot of time to do CPP check. Not a bad idea to just integrate it into your Makefile, into your make process. Right? It's a good thing. It's a good idea. You can even, I think it's enable equals all. Yeah. So, using the enable all flag, you can get even more messages. So some of these things are, like, once you've enabled all, you're not necessarily just getting errors, you're also getting stylistic advice. But that stylistic advice can be very useful. So stuff like variable x is assigned a value that is never used, and d, or %sign d in string number 1 requires int but is given argument of type double. Right? You shouldn't give doubles to int format strings, right? So it's extremely good. It's like having CPP check is like having a veteran coder who knows what the hell he's doing looking over your shoulder and saying, you shouldn't do that, you shouldn't do that, you shouldn't do that. That's fine, but don't do that. Right? Like, I would venture to assert that a fair number of the questions that we get about various things on Piazza, we wouldn't get those questions if the people who were asking the question ran their code through CPP check and made it compliant with the suggestions. Because very often it's because you've got arrays that are out of bounds and you don't realize it, or you're doing some sort of non-standard thing that's a bad idea, but you're doing it because you don't know it's a bad idea, because what the hell do you know? You've been doing C programming for what, like a month? So CPP check is it's like the crystallized knowledge of a veteran C++ programmer that's just available for you. So I can't say enough good things about it. But again, there are limitations. What exactly does it mean by, what do I mean when I say code being dangerous? So, it's like a general term that means the code probably doesn't do what you think it does. Right? And that's a problem in C. Like, out-of-bounds array access is a classic example of things not doing what you think they do. Another thing, like, another manner in which dangerous could be meant is it has a higher likelihood of producing an error, or it has any likelihood at all of producing an error. Like, the thing about seg faults is you only get a seg fault if you venture outside of your sort of your green zone, the memory block that the operating system gives you, right? If you've got an off by 1 error in an array, that means you're reading like 1 memory cell more than your array actually occupies. The number of times that's actually going to lead to a seg fault is relatively low relative to the number of times your program is executed, right? It's not going to crash all the time. In fact, it won't even crash most of the time, but there still exists within that code the possibility of crash. And you will have it crash eventually if you run it enough times. So, that code construct is dangerous, you know? But yeah, it's not dangerous in the sense that it'll set your computer on fire, or, you know, arm is going to grow out of your USB port and stab you in the chest. It's not dangerous in that sense, or it's not going to email all of your personal details to the U.S. federal government because they have them all anyway. That's not dangerous. You know, the danger is already passed with that. No, it's yeah. So that's what we mean by dangerous. Like stuff that you don't know, like it's not doing what you think it does, or it might cause an error. So yeah. So what does CPP check do? It detects common error patterns. It points out stylistic issues. It detects when code is dangerous. And specifically, it tells you stuff like out-of-bounds arrays, division by zero, useless conditions, unreachable code. So you can use CPP check to do similar types of checks as gcov, and a full listing is available at this link, which is, I believe, a forum post. Yeah, it's a forum post, maybe? Maybe it's a blog post? I don't know. At any rate, it's got all these checks for auto variables, booleans, bounds checking, function usage, classes. A lot of this applies to C++ rather than C, but of course, you know, C++ is a superset of C, right? So every C program is a valid C++ program. So all of these checks that are being applied for C++ are also applicable for C. That's why everywhere you see it's C/C++, you know? C itself is a very small language relative to C++. So, you know, if you're using C++ constructs, that's a different thing, right? But if you're not, then a C++ checker will also check for C. That's how it works. So it'll check, for example, that conditions are always true or false. It'll check, you know, I/O using string formatting, which is something we actually saw. It'll check for memory leaks. It'll check for null pointer dereferencing. And various other miscellaneous things like calculation with parentheses, assignment to a variable to itself. You're not supposed to assign variables to themselves. Like you've probably up to this point been like, well, why would I? Why could I possibly? You know, but you know. Wish you knew about CPP check for A1. Yeah. Ha. Well, now you know. Now you know. Yeah, it's like, again, it's like this thing I was talking about earlier. The more you know about programming, the easier programming becomes, right? But you know, yeah, it's just really useful software. But anyway, so yeah, here's this example that I already ran for you. There are lots of options for refining and customizing the analysis. For more, oh wait, I didn't do what it doesn't do. Let me back up. So this is the stuff that it does, right? But it's also important to understand the limitations of CPP check, right? So things it doesn't do. It does not detect all bugs. All right? It detects some bugs, but not all bugs. It does not compile your code or execute anything. It does not detect anything outside of the specified patterns. So, you know, this big list of things it checks, these are all of it doesn't check anything that it doesn't say it checks, right? It doesn't check anything outside of this. It doesn't check for anything that doesn't check for. I know that's a tautology, but give me a break. it does not detect semantic errors that are unrelated to getting the math wrong. So, for example, you know, if your program is well formed, but there's a semantic error with, if you misunderstood the question in the context of an assignment, right? Like, if it's like, oh, it wanted it in Fahrenheit, but I gave it in degrees Celsius, something like that, it's not going to be able to check for that because it doesn't know what your program is supposed to do, right? CPP doesn't check, it can't know what your program is supposed to do, so it can't check for that. It can only check to make sure that whatever you're doing it in accordance with the standards of practice for C programming, and you're not doing anything obviously wrong, like dereferencing a null pointer. So, also, what CPP check doesn't do, it doesn't replace testing or careful design. So you still have to write your programs well. In general, CPP check is it's not a replacement for being a good programmer. It makes you a better programmer. Like, in theory, you should learn from CPP check what stuff not to do, put that in your brain, and then not do it. So, like, as your career progresses as a programmer, you should need to rely on CPP check less and less, right? But yeah, anyway, so that's CPP check. Here's the last slide comic. First, there were batch files. They recompiled everything. It took forever. You got to take a long break while your project compiled. Then came Make. That was much more intelligent about what it built, but the scripts weren't portable between platforms. Then came Ant, which could build things intelligently and had scripts that were portable. Thanks, jerks. Writing scripts and waiting for compiles was the only frigging break I ever got to take. But Ant requires Java, so not in this course, baby! And, like, substitute Ant for, like, Docker and all of the rest of these similar compilation aid type softwares. Pieces of software. So, yeah. Boop. Credits. That's it. All right. Any questions? Chat has disconnected. Just when I asked for questions. Uh-oh. There you go. How hard is today's lab? Well, it kind of depends on how good you are at following instructions. Sorry, I'll give a non-facetious answer. Today's lab, Lab 7. Makefiles and testing. Well, if you were paying attention, it shouldn't be too bad. It's like the lab extends the knowledge a bit. Yeah. So basically, you download some source files. You produce a make file for it. It's more complicated than the one that we did in the slides, but not so complicated that it shouldn't take you too long to make it, I guess. And then you have to write some code that does the automatic testing using diff that we were talking about. So, yeah, I don't know if this one's actually a 4-hour lab. I could probably finish this in, 20 minutes to half an hour. So, 8-to-1 ratio is probably good. Yeah. And then lab 8 is, it's, basically lab 8 is you're going to be going through how to hook all of this stuff up into GitHub and get GitHub to, be able to run things like your Makefile automatically when you do things like push and like try to push something so that you can merge it, so you can make sure that the tests have passed before somebody tries to merge a branch back into main. Stuff like that. Should be straightforward, yeah, but, every time I think that something is straightforward, people tend to think that it's harder than I think it is, so, I guess I'll reserve judgment. But, anyway. Speaking of labs, why don't you guys go do your lab, and I'll go write your labs for next week. So, take care, take her easy, have fun, don't do anything I wouldn't do. Ta-ra.